bullet of mass lowercase m equals 10 grams is fired with a velocity v1 equals 300 meters per second toward a stationary block of wood of mass capital M is 3 kilograms and is rapidly brought to rest inside the block. The block is initially hanging from the ceiling by virtue of two massless strings as shown. What is the speed of the bullet and block just after the bullet is stopped? How high do the bullet and block rise relative to their initial height? The first thing we notice about this problem is that there is a collision during which the bullet embeds itself into a block. Whenever we see a collision, we recognize that conservation of momentum will certainly hold from the moment just before the collision to the moment just after the collision. And so we begin the problem by labeling two important moments, just before the collision to just after the collision. Whenever two objects collide, they may or may not conserve energy in this process. If they conserve energy in the process of colliding, what you will find is that the speed with which they recede from one another after the collision is equal to the speed at which they approached one another prior to colliding. If the collision is inelastic, then the speed that they recede from one another after the collision is less than the speed of the approach, and if the collision is totally inelastic, they don't recede from one another at all, which is the case here since the bullet winds up embedded entirely into the block. So we recognize that moment 1 to 2 will exhibit conservation of momentum, but will certainly not exhibit conservation of energy. Finally, in part B of the problem, we're asked what happens as the block swings upward, comes to a stop, and then moves down. During the process of swinging upward, there is no work due to a non-conservative force, and so moment 2 and 3 will be connected by conservation of energy. That means this is a mixed problem, with momentum being conserved from 1 to 2, but not energy, and energy being conserved from 2 to 3, but not momentum. Let's begin. Moment 1 connects to moment 2 via the law of conservation of momentum. Each time that we begin a momentum problem, we need to take a moment to recognize that momentum, as compared to energy, is a vector and not a scalar. If this is a multidimensional momentum problem, we will need to conserve momentum in each relevant direction. However, this is a one-dimensional momentum problem, and so we will only need to conserve our momentum in a single direction, which is the x direction. And so we solve this problem by stating that the momentum of the system at moment 1 is equal to the momentum of the system at moment 2. To find the total momentum, we need to ask object by object whether they have a momentum at the appropriate moment. So, at moment 1, does lowercase m have a momentum? Yes, it does. That's small m times velocity 1. And at momentum 1, does the large mass have a momentum? The answer is no, because at moment 1, the large mass is not yet moving. At moment 2, the bullet has become fully embedded inside the block, and so we no longer have a bullet and a block, but we have a bullet embedded in a block, whose total mass is lowercase plus uppercase m. And indeed, at moment 2, that object is moving, so we have a momentum at moment 2. Filling in the numbers that we know, we find that the only unknown in our momentum equation is the velocity of the bullet and the block at moment 2, and so we solve for this, yielding the result 0.997 meter per second. If energy were conserved from beginning to end in this problem, I would be tempted to connect the energy at moment 1 to the energy at moment 3, avoiding using any mistaken calculations we might have made in the first part of the problem. However, since we have an inelastic collision of the bullet with the block, we don't conserve energy between moment 1 and 2, and therefore our energy calculation is going to simply connect moment 2 to moment 3 Since there is no work due to non-conservative forces, we will analyze this using conservation of energy by setting the total energy at moment 2 equal to the total energy at moment 3. At each moment, we need to ask ourselves 3 questions because we know of 3 forms of energy. At moment 2, do we have translational kinetic energy? Yes, we do. 1/2 the mass of the object at moment 2 times the velocity at moment 2 squared. At moment 2, do we have gravitational potential energy? That all depends. Gravitational potential energy is mgh, or as I prefer, mgy, and we get to set the y of the coordinate system wherever we like. Since it is typical to set this at the lowest point of the motion, we'll call the y equals 0 point to be moment 2, and so we have no gravitational potential energy at moment 2. Spring potential energy at moment 2? I don't think so. There are no springs in this problem. Asking the same 3 questions at moment 3 will complete our equation. At moment 3, do we have kinetic energy? No, we don't, because the object is momentarily at rest. At moment 3, do we have gravitational potential energy? Yes, we do, because it is raised above the initial starting height of y equals 0. And so this will give us total mass of the object times g times the y value at moment 3. Finally, there are still no springs in the problem, and so this completes our conservation of energy equation. We recognize a very convenient cancellation, that the total mass of the object will cancel on both sides of the equation, so that y3 is simply written as velocity 2 squared over twice g, which yields the result 0.051 meters.